Hello. Okay, so this is working. Hi, I am Vishal. I am a software engineer at Google. I work in the load balancing team where we try to solve the load balancing solution problems for Google services and also for Google Cloud customers. Some of the learnings that we've had over years we'll see in this presentation, but this presentation will primarily focus on load balancing for a large service. We are not going to cover a lot of basics of gRPC load balancing because this is something that has been covered before in KubeCon 18 by my colleague Jan. If you have any questions, we can talk about it at the end of this presentation. Jan is here, so you can ask him those questions. So what do I mean by a large service? A large service is generally a service which has a lot of clients, a lot of requests that the clients need to make, and generally clients which are distributed pretty much globally. So when we talk about the problems and we talk about the things that we want to care about, when I say large services, it's the aspect of the service that I'm going to talk about. So we have a small agenda for this presentation. We'll look at load balancing in gRPC at a very high level, go quickly over it, then talk about centralized load balancing, what does it mean, and how all that goes into load balancing at scale, and then we'll look at service mesh and how does that work with gRPC services. So why load balancing? I believe I don't need to talk a lot about that, but generally, load balancing is used to improve a throughput of a service. So if you have a very large service, you would need multiple endpoints or backends for that particular service, which can serve those clients so that you can scale. And it also means that the more endpoints you have, it increases your service reliability and availability. These are important for load balancing, but outside of that, there are a couple of other things that load balancing needs to worry about. One is the client requirements. You can't really have clients connect to all your endpoints, for example, or the client is latency sensitive. So how do you need to load balance looking at the client characteristics? Also, you need to look at endpoint or the backend requirement, whether it needs isolation or protection of certain format, which for most large services is true. And also, if there is a lot of connections from clients, how do you really make sure that only a portion of clients connect to them and don't overwhelm the endpoints? So let's briefly look at client-side load balancing in gRPC. In gRPC, we have two load balancing algorithms, which are round robin and pick first, which basically pick a set of backends or a single backend based on the discovery or the resolution of that endpoints. So based on the load balancing policy, the client can decide to pick one endpoint and just use that endpoint for all its requests, or round robin over all the endpoints that it has received. Optionally, the client can also connect to a subset of endpoints. We don't have it in gRPC, but this is one of the aspects that can be completely controlled on the client side. So at the client side, you have certain control over what endpoints you can select and how you can select it, and that can basically help you to limit the number of connections a client can make, and can be used to enable the level of client behavior that we've seen previously. But just making decisions on client is not really helpful in a bunch of scenarios. For example, if you do decide to use pick first, now in this particular case, because all the clients are taking decisions independently, a bunch of clients, or maybe all of them, end up connecting to a single endpoint, which can overwhelm those endpoints and bring those endpoints down. This can eventually cascade to bring all the endpoints down. Now, that's definitely not desirable. Also, round robin is not really great. If a single client has a lot of requests to make, and maybe it is buggy, or maybe it's a form of attack, eventually bring down your whole service. So just making decisions on the client side is not enough. You need more. So this is where a centralized load balancing really helps. A centralized load balancing can essentially determine what endpoints a client can connect to. Now, this is more than just the discovery that we've seen previously for client LB. And in this, the load balancer actually knows about what clients are available and can tell each of the clients what endpoints to connect to, and the clients can eventually take their own local decisions to connect to those endpoints. In this particular example, you can see that the load balancer actually ended up giving even number endpoints to one of the clients and odd number to the client too. So it can help provide isolation to those backends and protect them in case one of the clients really starts overwhelming the service, and still allow the other client to continue to serve. Now let's look at an example of centralized load balancing. I'm sure most of you have already looked at gRPC or gRPC LB. Now gRPC LB, the way it is right now, is a protocol to provide endpoints to the client from a centralized gRPC LB server. Now this is called lookaside load balancing because this is purely a control path load balancing where your actual connection from client to endpoint is directly between them, and there is no control part aspects of this. There is no hop. And we'll see another example after this, which is the proxy load balancing, which has a hop in between, which is slightly different. But in gRPC, the gRPC LB essentially picks the endpoint that is sent to the client. Right now, the default for client with gRPC LB is round robin, and the balancer essentially provides a weighted endpoints to the clients in the form of repeated lists. And we'll look at a little bit more in terms of how those weighted endpoints impact the clients and why they are needed. So gRPC LB is the first example of your centralized load balancing. Another example that is commonly used is proxy-based load balancing. For this presentation, I'm purely going to talk about Envoy as a proxy, and I know there are a lot of other load balancing proxies available, but we are talking about Envoy because it's one of the most popular ones. For this presentation, we'll only worry about the load balancing aspect for Envoy and not of other capabilities that a proxy provides, and you might want to use it for those reasons. But from a load balancing point of view, an Envoy proxy connects to management server. In this particular case, I have shown you an example of Istio Pilot, which serves an XDS load balancing API for Envoy. So the Envoy connects to management server to get the endpoints that it needs to talk to, and then uses that to route the request to the right endpoints. The client over here, in this case, the gRPC client, doesn't really know about all these endpoints, and it basically the connection gets terminated at the Envoy proxy, and subsequently the Envoy proxy does the load balancing for those endpoints. The Envoy itself can be deployed in a middle proxy or a side proxy mode, and in this particular example, we are using a sidecar. It's again one of the most popular methods of deployment. Now we've talked about how a centralized load balancer can allow you to provide isolation such that your servers are protected. But that's not enough. There are more deployment considerations for a large service. One of it is your endpoints themselves are heterogeneous, and they can be heterogeneous in various aspects like their capacity. We'll talk about what capacity means a little bit later when we talk about it in more detail. Also in terms of location, endpoint could be in a geographically different location than a client, or endpoints can be globally distributed. But they are heterogeneous to the point where a request made from a client will have a different behavior when you reach out to different endpoints. Also, endpoints' health and capacity can change over time for various reasons. You are upgrading your service, or there's a hardware failure when you are actually dealing with physical machines, which can change the capacity over time. There are other aspects too, like request could not mean, not every request is the same, and that could impact your service capacity and availability. So looking at just the endpoints and making decision without really taking endpoint information into consideration is not really great. And that is where we need to start thinking about centralized load balancing, having to get those information to make better decisions. So what we're essentially trying to say is, for informed load balancing, we want the backends or endpoints to start reporting information to load balancers. Now, what are these kind of information that you would need? we talked about capacity. What is capacity? A capacity is essentially service specific and can be various aspects. It could be number of RPCs that your particular service can or the endpoint can serve, and that can differ based on how big your endpoint is in compute or in memory. It can also differ. It can also be something like your utilization of and aspect. And one of the good example of this is the gRPC load reporter protocol, which allows you to report all of this back to the balancer. And I believe open source implementation for this exists, at least in C++. I'm not sure about other languages, but this is something that you can use to provide more information to the balancer such that the load balancer can make better decisions based on endpoint capacity and provide those to your clients. We saw in gRPC example that the gRPC LB just gives you a list of endpoints that clients round robin over. Using your capacity, the load balancer can actually give weighted information where it could repeat some servers, indicating to the client that you can do more RPCs on those endpoints as it has more capacity. One other important information that a load balancer can use to a centralized load can use is the health of an endpoint, whether the endpoint is up or not. So instead of giving an endpoint which essentially doesn't serve anything, it could really give an endpoint which is serving right now. And these are more timely information, thus allowing the clients to be able to do their requests and get a successful response. Second aspect of informed load balancing is locality. Now, what is locality? I talked about large services where clients are distributed all over the world. For the behavior of the service that you expect, you would want those endpoints to be also distributed across the globe, which means there is an advantage for your clients to reach out to endpoints which are more local or closer geographically to them. But to actually do that, you need a construct to allow the load balancer to inform the clients that these are the servers that you need to connect to. So I've shown an example of a couple of locations over here. So the construct of where an endpoint resides needs to be made available to the load balancer and also needs to be made available to the client in some format. Either it can be encoded as part of the protocol like in gRPC LB, or it could be done as part of a protocol which XDS does, wherein it provides locality as an explicit member in the protocol, where the client can take more informed decisions about where it wants to go. And the advantage of this is the client can take advantage of spatial locality and have latencies, reduce latencies for the request. This kind of locality is different from the temporal locality associated with PIC server that we've seen before, where a client would want to reach to the same server again and again. Also, the other advantage that a locality gives you is it can give you an abstract concept of locality capacity that can be used for smarter balancing at the load balancer. For example, a bunch of servers' capacities can be aggregated for a particular location, and you can say a particular location has a certain capacity. This allows the load balancer to basically balance based on those capacities. And we'll see how this becomes more relevant when we move on to the next slide. So we talked about a bunch of concepts till now about what is required for load balancing at scale, how to make centralized load balancing, have more information such that it can do smarter decisions. Now, assuming we do all of this, what does the real architecture look like? This is a mocked up load balancer, but it tries to illustrate what exactly we've talked till now. You have multiple locations A to Z, and you have a bunch of services. All are reporting their load back to the load balancer, and the load balancer is basically making global decision for each of these services, and at the same time sending those information to the client, where it's telling client what to do based on those capacities, weights, localities, etc., trying to serve it closer to the clients. All this calculation will take will take some time because it's purely depending on your scale and number of services. But is this the right way to do? Maybe not. Maybe there's something additional that we could do, which is we could divide the responsibility between the centralized global load balancer and the client. We could have the centralized load balancer take some of these decisions, while the clients can take more decisions more locally based on the information that they have. The global decisions like what's the capacity of a particular locality and where is, for clients in particular locality, where should they directly go to, those can be made at those decisions can be made globally at the load balancer, while the clients can take more local decisions of which servers to pick and which localities to pick in case certain localities fail. Now, this is not really possible in gRPC LB protocol. gRPC LB protocol doesn't really have the information of locality encoded in it, but this is something which already exists in XDS protocol and is already available with in the form of locality and endpoints. Now, let's look at service mesh and load balancing and how it happens. This is a small example of what it would look like for two services, service 1 and service 2. Service 1 is deployed in 2 locations, USA Central and Asia South, and service 2 is deployed in Asia South and USA West. Service 2 is a client which wants to connect to service 1, and based on locality, all the services are sending load reports to Istio pilot, and it's making load balancing decisions and giving the information to the sidecar proxies for load balancing. So whenever a client from USA West wants to connect to a service S1, it is redirected to a server which is closer to it, which is in USA Central, while the servers from S2 are redirected to Asia South, except for one server, because the capacity in Asia South, as indicated by the number of servers, which is just 2, is not enough to serve those requests. And for that particular server, which in our case is server S23, it is redirected to USA Central. So this way we can achieve multiple level of load balancing, where clients can locally go to closer servers, while globally the Istio pilot or a management server can basically redirect them to a different locality. Now, we've talked about gRPC services and we've looked at service mesh. Now, this presentation and service mesh. So how do they come together? The same infrastructure that we've talked about for service mesh using the sidecar proxy can also be used to do gRPC load balancing. And we've looked at how XDS provides various constructs for load balancing flexibility, including locality and proximity information. These information can be used to do gRPC load balancing using the sidecar. And we'll look at that in our demo, which we are going to do next. So this is my demo setup. In my demo setup, I have something similar to what we have seen before. The only difference being only the clients are the only ones that are using the sidecar, while the endpoints are not using sidecar. And the only information that the endpoint is really sending is the health information associated with that endpoint. I've not configured a capacity for this demo, and the health is the only information that is going to be used for global load balancing. Now, in this particular case, similar to the previous service mesh architecture or deployment, I have a greeter service and a greeter client. The greeter service is actually deployed in USA Central and South Asia, each with 2 instances of servers running. And this deployment is set up in GC with traffic director as the management server. We can use Istio as the management server too. Traffic director was just easier for me to configure for this particular demo, and it's easier for me to write up a demo script, which I've also made available and is present in the last slide. So, but it's the same XDS API which Istio uses. So for this particular case, I have greater service with 2 endpoints running each in USA Central and South Asia. And I have greater client, one running in USA West and one running in South Asia. So by default, whenever the demo starts, you'll see that the greater client basically reaches out to greater service in USA Central, and greater client will reach out to service the endpoints running in South Asia. So let's look at the demo. So these are my machine names. They are slightly different from what is in the demo. From a configuration point of view, they are managed in each of them are all of these are under one particular service, and I'll show. Maybe this is not the right way to show it. Here. So I have this one service which is configured, which is right now shown as healthy because it has all the endpoints associated with it as healthy. And I have 2 clients, which just open another console for this. So I have 2 clients, one in Asia and US West. What I'll show you is, let me first start the clients on each of my nodes. So all the server does is respond with its name, which has its continent, which region it is from, and its actual host name. On the client side, outside of making the actual requests, I have a HTTP server running, which basically displays what the last 50 requests, where the last 50 requests have gone. I have 2 of them. As you can see, this is US West. It's for the last 50 requests have all been in US, and for Asia South, all last 50 requests have all been in Asia. I need to refresh this because this is a pretty basic HTML page that I could cook up based on my HTML expertise. So as you can see, they are all last 50 requests are equally divided on 2 nodes. Now let's bring one of the server down and see how the client react to them. Okay. Mm-hmm. So I've stopped the service on one of the nodes in Asia South, and we'll see how it impacts the requests that are being made. So ideally, in this particular case, once the service goes down, the management server over here detects that it is unhealthy, and it will start to redirect some of the traffic to a different node. So it's already started to do it on US Central. Okay, I think I've brought down both of them. So So in my frenzy of typing, I ended up bringing down servers on both the continents. So let me try it again. So in this particular case, because one node went down on each of the continents, you see that both the clients, the US West client and the US and the Asia South client, end up making requests across the continents. You would also see, at least in this dashboard, right now it will show only one as unhealthy because I have brought the other server up. So it's unhealthy. So you can see that the one server has gone healthy. Now let me start the gRPC server again on US Central. That should change the way the requests start routing. Okay, there it has started routing again to that particular node. So you see, as soon as the node came up, the load balancer basically ended up informing the client, the gRPC client, to start moving traffic back into US Central. This is for the US Central. So the US clients are now all being served in one region, while the Asia client still has one node down, so it's moving traffic from Asia to US. So a bunch of these demo scripts are available in the GitHub repo. You can all try this yourself. It just took 7 steps essentially to get the setup up and running. So if you really want to try out for yourself how to do this global load balancing and trigger behavior and get hands-on experience on doing it, you can use those scripts. The server that I have is pretty basic. It's Greater server. It's one of the most common examples of Go server available. You could build your own server and replace that, and it will still work the same. You could try it with more complicated setup. As I mentioned before, the gRPC specific load balancing presentation and the examples, if you want to take a look at it, are present in the second link given below. And yeah, you could try those out too. So that's all I had today. If you have any questions around things that we have talked, you can ask them now. Yeah.
Hi, question about long-lived connections with gRPC. So load balancing works well on the initial connection, but if you have a long-lived, how do you handle rebalancing?
Yeah. So long-lived connections are definitely a problem when you are thinking about capacity for a particular server. So for long-lived connection, unfortunately, the biggest decision maker is going to be the centralized load balancer, because the client cannot independently make a decision. In this particular case, your capacity cannot be derived based on your RPC request, but in essentially how much resources are utilized at your server. So if you can plug that into your load balancer, you could definitely you can definitely use that information to set the load balancing weights in your XGS protocol to make sure the next set of requests are coming from, are going to different servers. So that's definitely possible. It's a little more trickier than just single RPCs.
Any more questions? Going once? If I'm not seeing you, wave louder. No? Okay. Thank you very much then, Vishal.
Thank you.